figure below shows a small mass resting on a ramp. The ramp is free to slide horizontally across the table, and the small mass is free to slide frictionlessly up or down the ramp. By pushing on the ramp with the force S, you can cause the system to accelerate. With just the right value of the force, the block will neither slide down the ramp, i.e., with more force the block would slide up the ramp, and with less force the block would slide down the ramp. Find all the following: acceleration, force necessary, and the normal force. You can smell it. This problem looks like it's got some sort of a trick. Your imagination says, "Oh no, what am I going to need to do to solve this problem?" The answer: exactly the same thing you do on every other force problem. Free body diagram, align the coordinates, sum the forces to MA, and you're done. So let's begin. I'll highlight the 2 kilogram mass in red, and I'll also highlight the 5 kilogram ramp in blue. Let's begin with the 2 kilogram block, and as always, the first step in every force problem is draw a free body diagram. That dot represents the 2 kilogram mass. The first force we think of acting on the 2 kilogram mass is gravity, which will be 2 times g, which is downward. There are no strings for tension, but there is a force underneath the 2 kilogram block. In this problem, there is no friction to be found anywhere, and so, as a result, the only force that the contact surface can provide is a normal force, and we'll call this one N1 because there are actually 2 surfaces in the problem overall. And that's it. The 2 kilogram block experiences gravity, and it experiences a contact force because nothing else is applied directly to the 2 kilogram block. Now at this point you might be tempted to draw a coordinate system which is aligned with the ramp itself, as you often do with a block on the ramp. That would be incorrect. Let's remember the principle by which we always align the coordinate system in our free body diagrams so as to make the equations most simple. We align the coordinate system with the acceleration. Since when pushing just right on the system, the red block will neither slide down near the front of the ramp nor up towards the back of the ramp, but instead move directly horizontally. The acceleration is in the horizontal direction. And so we decide to create the coordinate system with the plus system, plus to the right, and then finish it out. Thus, we recognize in this problem that the 2g force is along the coordinate system, but N1 is not. This means that N1 is going to need to be broken into components, and what we're going to need to do to accomplish that is find where this 30-degree angle is located in our coordinate system. So, how do we do that? We recognize that 30 degrees represents the angle between a horizontal. Oh good, we've got that in the coordinate system. There it is along the x-axis. And a diagonal at the angle of the ramp. We don't have that in the coordinate system, and so what we do is we simply draw it in. This green line represents the angle of the ramp. So we recognize by inspection that this green line will have an angle of 30 degrees to this horizontal axis. If that angle is 30, then this, which makes up the rest of the right triangle, must be 60. And so finally, the angle in this corner is 30 degrees. We can then write our two components of the force N1. We follow one of the axes. I think I'll follow the y-axis first. And we follow this axis until such time as finishing the triangle results in a right triangle with the second component perpendicular to the other axis, which is x. Looking very carefully, we see that the side opposite to the 30 degrees will be of size n1 sine of 30, and that the side adjacent to the 30-degree angle, that one over here, will have a size of n1 times the cosine of 30. So n1 sine 30 will appear in our x equation, and n1 cos 30 will appear in our y equation. Let's begin the problem by analyzing the y direction where there's no acceleration. We'll call the plus direction for y upwards, in which case we will have n1 cos 30 as the positive force, 2g as the negative force, and there is no acceleration in the vertical direction. The acceleration is purely horizontal. This equation, as you'll notice, has only one unknown, and so we can simply solve for n1. n1 is equal to 2g over cos 30 which is 22.6 newtons. And that's our first answer. We're not done with this free body diagram because we need to analyze it to find the force in the x direction. In this case, there's only one force in the x direction. That one is n1 sine of 30. And the sum of the forces in the x direction, since there is an acceleration, is m, which is 2 kilograms, times a. Since we solved in the previous step for n1, we can simply plug in that value and then get the final result that a for this system is equal to 5.66 meters per second squared. So far so good. We're entirely finished with the small red block, and so now we need to turn our focus to the 5 kilogram ramp. Remember, there is no friction in the problem, and so the 5 kilogram ramp is free to slide horizontally across the table, and it sure does. This dot will represent the 5 kilogram ramp, and now we need to list each and every force that's acting on it. Well, the first thing that acts on it, we can imagine, is gravity. That's m times g, so it's 5 kilograms for the ramp times g. And then we notice that this ramp experiences two contact forces, one between the ramp and the table, and the other between the ramp and the 2 kilogram block. Let's deal with the ramp and the table first, because that's the one that's more familiar, and that will give us a force N2 in the upward direction. The other contact force is the force between the ramp and the block. Here we're going to call upon Newton's third law in order to understand what that force is. Looking back at the diagram for the 2 kilogram block, we notice that one of the two forces in that diagram can be considered to be the force of the ramp on the block. And the force of the ramp on the block is N1. Newton's third law says the force of the ramp on the block is equal and opposite to the force of the block on the ramp. So, if we have N1 up and to the right, acting on the block, we must have the same amount, N1, down and to the left, acting on the ramp. Finally, we have one more force. We've accounted for gravity, and two surfaces of contact, but we're pushing the ramp to the right using our force capital F, and so we draw that into the free body diagram. As always, the principle by which we orient the coordinate system in any free body diagram is that the coordinate system will be aligned with the actual acceleration. This leads to the simplest possible equations as a result of our free body diagram. Since the ramp accelerates directly to the right, we will make the plus direction to the right, meaning minus is to the left, and then the perpendicular to that will give us the second of our two coordinates, and that will be vertical. Notice in this free body diagram that although the 5G, the F, and the N2 are nicely aligned with the coordinate system, the same cannot be said for the force N1. N1 we need to make into a triangle. We'll make that triangle by following one of the axes. I'm going to follow the y-axis, and I will go downward until finishing the triangle, making a pretty right triangle, is done in parallel to the x-axis. What we need to do is we need to place inside this diagram the angle 30 degrees. We notice that in the diagram to the left, 30 degrees is the angle between N1 and the vertical portion of the coordinate. Since the force in the right-hand diagram is equal in strength and opposite in direction, by analyzing vertical angles, we find that the 30 degrees is found in the top of this triangle, meaning that the two sides, the one opposite to the 30 degrees is going to be N1 sine 30, and the one adjacent to the 30-degree angle is going to be N1 cos 30. So just as with the set of equations for the red block, we will have N1 cos 30 in one equation and N1 sine 30 in the other equation. Now let's proceed. Beginning with the y-coordinate, for which we'll call up as the plus direction. It doesn't matter because there's no acceleration in y. We will say that N2 is the only force in the plus direction. However, in the minus direction, we will have N1 cos 30 as well as 5G. Since the acceleration is only in the horizontal, the sum of the forces in y is 0. Since N1 is known to be 22.6, we can solve for N2 and get N2 is equal to 68.6 newtons, which happens to be equal to 7 times g. You could have anticipated that, recognizing that the table has to hold up both the ramp and the block. Finally, there's one more direction to analyze, and that's the horizontal direction. So in x, for the blue ramp, we will find that the force in the plus direction is F. That's still an unknown. However, in the minus direction, we have N1 sine 30. That's it for horizontal forces. The sum of the forces in the x direction, since there is an acceleration, is equal to m, which is a 5 kilogram ramp, times the acceleration a. However, in this equation, we notice that N1 is known from the previous problem as 22.6 newtons. A is known to be 5.66 because the ramp and the block move together. They have the same acceleration. And so the only unknown in this expression is F. yielding F is equal to 39.6 newtons. Not so scary after all, as long as we keep our heads. Isolate each object, draw a Freebody diagram, and align the coordinate system with the acceleration, and yet again, this problem is no different and no more difficult than any other force problem. Just don't be scared.